The Heisenberg uncertainty relations is enormously general. It applies without saying anything whatsoever about the nature of the particle, how it is prepared in an experiment, what it is doing, what it might be interacting with. It is clearly a profoundly significant physical result, but at its heart it is simply a mathematical statement about the properties of wave that flows from the assumed wave properties of matter plus some assumptions about the physical interpretation of these waves. There is a little indications of what the physics might be that underlies it. One way to cover what physics might be present is to study what takes place if we attempt to measure the position or momentum of a particle. This is in fact the problem initially addressed by Heisenberg and leads to a result that is superficially the same as we have discussed in the last equation. This is in fact the problem initially addressed by Heisenberg and leads to a result, but from a physics point of view, there is in fact absolute difference between what Heisenberg was doing. Heisenberg analysis was based on a thought experiment. That is, an experiment that was not actually performed, but was instead analysis as a mental construct. From this experiment, it is possible to show by taking account of quantum nature of light and matter that measuring the position of an electron results in an unavoidable, unpredictable change in its momentum. More than that, it is possible to show that if the particle positions were measured with ever increasing precision, the result was an ever greater disturbance of the particle momentum. This is an outcome that is summarized mathematically. In his thought experiment, Heisenberg considered what was involved in attempting to measure the position of a particle, an electron, say by shining light on the electron and observing the scattered light through a microscope. To analyze this measurement process, arguments are used which are a curious mixture of ideas from classical optics, the wave theory of light, and from the quantum theory of light, that light is made up of particles. Now we take a little look on diffraction. Look at this picture. This picture describes the diffraction patterns. There are two images, and these images are called diffraction images. Diffraction images A and B corresponding to two extreme possible positions of a point object scattering a single photon that arrives at point C. You can see in the figure. If one photon strikes the image plate, the point C where it arrives could be anywhere between two extreme possibilities. On the extreme right of the central maximum of a diffraction pattern, which is labeled A. And this pattern will build up by many photons scattered from a point objected at position A. Or on the extreme left of such a pattern, which is labeled as B, built up by many photons being scattered from a point object which is positioned as B. With 2 delta x, the separation between A and B. Here 2 delta x is the separation between A and B. The best we can say after detecting one photon only is that the object that scattered it was somewhere in the region between A and B. That is, we can specify the position of the object only to an accuracy of plus minus delta x. Now we turn to the experimental interest, namely that of measuring the position of an electron presumably placed in the viewing range of the observing lens arrangement. In measuring its positions, we want to make sure that we disturb its position as little as possible. We can do this by using light, whose intensity is as low as possible. Classically, this is not an issue. We can turn down the light intensity to be as small as we like. But quantum mechanics gets in the way here. Given the quantum nature of light, the minimum intensity possible is that associated with the electron scattering only one photon, as we saw in the previous section. This single scattering event will enable us to determine the positions of the electron only to an accuracy. The size of an atom. Here we will discuss about the size of an atom. One important applications of the uncertainty relation to do with determining the size of atoms. Recall that classically atoms should not exist. The electron must spiral into the nucleus, radiating away their excess energy as they do. However, if this were the case, then the situations would be arrived at in which the position and momentum of the electrons would be known, stationary and at the position of the nucleus. This is in conflict with the uncertainty principle. So it must be the case that the electrons can spiral inward no further than an amount that is consistent with the uncertainty principle. To see what the uncertainty principle does tell us about the behavior of the electrons in an atom, consider as the simplest example a hydrogen atom. Here the electrons is trapped in the Coulomb potentials well due to the positive nucleus. We can then argue that if the electron cannot have a precise defined position, then we can at least suppose that it is confined to a spherical shell of radius a. Thus the uncertainty delta x in x will be a. And similarly for the y and z position. But with the electron moving within this region, the x component of momentum will be px. X will be written in the subscript. Will also be symmetry, swing between two equal and opposite value p and minus p, say. And hence px will have an uncertainty of delta px, which is approximately equal to p. By appealing to symmetry once again, the y and z component of momentum can be seen to have the same uncertainty.